Hi, in this video we will perform the analysis regarding a very important data reduction technique that is known as principal component analysis, and for that we'll be using two important libraries. One is FactoMineR and factoextra, and apart from this we'll be using a library which is known as metan to create a correlation plot. And to perform this kind of analysis we'll be using a data set which has got 32 entries, in fact 32 genotypes based on different variables: root length, root yield, dry matter, number of leaves, shoot length, root length, and total carotene. This data set is based on 32 different genotypes of carrot, and it is taken from Khan and Mir. Then the first important step to perform the analysis to see the labels of our data. Either we can use the function view, or we can use the simple this function names, then followed by the name of this data set. Then we will click on this run option. Then you can see we have the names for different data set. In order to see the dimension of the data, how many number of rows, how many number of columns we are having, we'll simply write dim followed by the name of this data set. Then I will click on this run. Then in order to create a correlation plot, a Pearson's correlation plot among the variables, we'll be using a function that is coef. Like if I will write here corr underscore coef, it creates a linear partial correlation among the variables. Then I have to write the name of the data set. Then I will use these square brackets, and I will write 2:7. The reason is that I want to make a plot, or I want to create a matrix of correlation between the variables which are continuous in nature, because in order to we can only get the value of Pearson's correlation provided we are having the variables which are continuous in nature. So from second, third, fourth, fifth, sixth to seventh column we are having the continuous variable, since the first variable is a categorical one. Then I will click on this enter. We are having a correlation matrix of these among these six variables, and you can see we are having a good amount of correlation, greater than 0.5, and which is quite a good figure in case of correlation, in case of principal component analysis. Because in principal component analysis, an important step is that if you are having the large number of variables, we are dealing with a large number of variables, the important thing is that there should be a good amount of correlation, a good amount of correlativity. Then only we can proceed. If there is a very low amount of correlation among the variables, then we don't need to go for principal component analysis. Then if we want to create the plot of this, we will simply write plot followed by this bracket. I will close this bracket, then I will click on this enter. So we will be having this type of a plot. That is why this metan library was used, and you can see the correlation between dry matter and total carotene is quite good, 0.55, and it is significant, and almost all these correlation between the variables is greater than 0.5. So we are good to go. But in order to proceed the correlation principal component analysis in R, the first important step is that we have to create a matrix of our data set. So for that we will use this data.matrix for this data set. So we have already written this function here in our console. We'll click on this run option. Then since we want to create, we want to portray these rows, since every row is represented by a different genotype, so for that we'll be using this function. Then click on this enter. Then this -1, it is nothing, it simply says us we'll give the name to this. Suppose we'll write anything, then followed by assignment operator, and I will again write this new data, then put these square brackets, comma, -1. Since we have to perform the analysis based on these 6 variables, since the first variable is my genotype, so in order to exclude that, So that is why we will put minus before the position of that variable. Then if I will click on this add new data, it will give us the results regarding some first few rows and few columns. Now in order to perform the basic this principal component analysis or PC analysis in this R, for that we will use a default function, that is PCA, which performs the principal component analysis with supplementary individual, supplementary quantitative variables and supplementary categorical variable. The first thing here is that we have to write the name of the data set. Then scale.unit is equal to true, that we have to normalize, or we can say to standardize the data. Then we'll be using this graph is equal to false, since if I will write this true, then it will create this black and white graph. So for that I'll be using a named a function followed by the like res.pca followed by is equal to, or you can write the default this assignment operator, then followed by this default code PCA, then the name of the data set, then enter, then comma, scale.unit is equal to true. If I will write again this scale.unit like this, scale.unit, see the data are scaled to the unit variance. Since we are having different variables and each variable is measured on different scale, so in order to standardize them, the unit variance will be using this function. Then I will write graph simply is equal to false. If I will write it true, then it will create me a graph which will be in black and white form, which I will show you. First I will click on this enter, then I will write again this function. If I will write this as true and I will click on this, so here you can see we have some plots which are not quite good. This is not a good visualization actually. So in order to overcome this, we'll be using this as false. So we have made a function. We will simply write summary res dot pca and click on this enter. So we have the results here. So we have the results for eigenvalues, which are nothing. These are the variances of principal components, and we have 6 components. Since original variables were 6 in number 1, 2, 3, 4, 5 and 6, actually this principal component analysis, what it does, it transforms the original variables into the number of components. Say for example, the number of components are equal to the number of variables. We are having 6 variables, so we have 6 these components. And how we are going to retain a particular component? For that we will be using this the value eigen values, and the thumb rule is any eigenvalues greater than 1 is to be retained. Since only the first component's eigenvalue is greater than 1, so only this one is retained. So in order to proceed, I will again write res.pca to make it very simple. I will write this $sign followed by this eigenvalues. Here you can see the eigenvalue for the first component is 4.42. Only this one is retained, and this is single-handedly explaining 73.73% of the variation. If I will again write this res.pca, then I will put this $sign. I will click on this var. We'll get the results of each and everything. The first is for the coordinates. Then we have the results for the correlation. That means the correlation of each and every variable with respect to the component. Say the correlation of RootYield with respect to component first is 0.9, and similarly you can interpret the others. Then we have the quality of representation of each and every variable with respect to the component. Since we are mostly focused with this dim1 or component 1, because it's having a eigenvalue of greater than 1, and it is contributing almost 73% of the variation. Then we have the contribution of each and every variable across these components. Then we'll make a plot which is known as scree plot. For that we'll be using this fvz_eig, then followed by the name of this function which we have given to this PCA. Then we will click on this run. We'll be having a scree plot, and you can see that 73% of the variation or the variance is explained by the first component, and it is also known as the elbow plot since it gets decreased like in this way. Then we want to have another plot. For that we'll be using this phys pc_byplot. It will create a byplot where we'll be having the display of these like col.indices into red. We are giving red colors to the different genotypes. I will click on this run again. Then we'll be having a plot here. You can see these red colors, these are nothing, these are the genotypes, and you can find out that C80 and Chaman are good, in a sense the best genotypes among the rest of the genotypes if we are interested to choose these genotypes. But since this is a column wise analysis and we are mostly interested to choose a variable which is contributing more, for that we'll be using this function. This function will be using, that is phys_var, and for that we'll be using different colors, and we will see the quality of the representation. Then we'll click on this run. Then again we'll be having a byplot for that. So here we can see these are having, it is having a horizontal line and a vertical line. In horizontal axes we are having component first with respect to the component second, and the circle is nothing, it's a correlation circle, and these arrows, they represent each and every variable, and closer these arrows are towards the circumference of the circle, the more important that particular variable is. Like we have good, if we want to choose which of the variables are contributing more, we have RootYield, we have root length, we have shoot length with respect to the component first. Similarly with respect to the component second, we can see, and this color represents the quality of the representation of each, and here the quality of representation of this total carotene is more. But if we want to see the contribution is more regarding to these variables. And the good thing is that this range is from -1 to +1. That is why it is known as a correlation circle, since the range of the correlation coefficient is from -1 to +1. And if we want to see the contribution, then we're using this function phys_contribution. Then with respect to first, if I will write x is 1 with respect to first, and top 6, since we are having 6 variables, I want to choose which the variable is important. So among these 6 with respect to the component first, we have RootYield, root length, number of leaves, DryM matter. And if we will write 2 here, and I will write here 6, say 6, I will click on this run, enter. We have total carotene and shoot length, which is already displayed here. This is with respect to component second. We have total carotene and DryM matter, which are very important with respect to component first, like in this contribution plot. And with respect to component first, we have these 2 4, and with respect to component second, we have these 2. So instead of taking all these 6 variables into account, so we have only 4 variables which we have to retain, or which we have to extract from these 6. Hope you like this video. Please press the bell icon and like the video. Thank you.